So chapter 2 is going to be on logic. And the main idea we're going to have here in logic is we're going to want to use some things that we know to deduce new information. So that's sort of the basics, right? We're going to have some set mathematical rules that we accept as fact, and then we're going to build off of those to create new rules. And we're going to try to understand how this process works. That's the goal of this chapter. So we've got a little logic puzzle here. Perhaps this is one you've heard before. You've got a fox, a chicken, and a sack of grain. You want to cross the river, but you can only take one of them with you at a time. You can't leave the fox with the chicken. You can't leave the chicken with the grain. And we want to know some way to get all three across, right? So we just have to think about what we know, make sure we're sort of putting these pieces together. So what we're going to do in this section is think of a mathematical way to do that. If anybody wants a little extra challenge problem, you're welcome to write up a solution to this one. And just type that up in Overleaf, post it on Campus Wire, send it to me, and you can get a challenge point for that. All right, so where are we going to start with this discussion? We're going to start in section 2.1 with statements. So statements are just going to give us sort of a structure where we can actually start working with logic. Right? Logic is about proving things true, so we need a statement to just be something that you can actually decide if it's true or false. So a statement is a sentence that is either definitely true or definitely false. So let's go through and give some examples of things that are statements versus not statements. So perhaps you can think of some on your own, and then when you're ready, come back and look at this. So we can say things like a statement, right? Doesn't necessarily have to be true, but has to be provably true or false. So I could say every even number is divisible by 2. That is either true or false. In particular, it is true. So that is a statement. I could also say every even number is divisible by 3. That is also a statement because these are true or false. But in this case, right, it's false. That's fine, it's still a statement. I could say the square root of 2 is a real number. That's a true statement. I could say the cardinality of the set 0, 1, 2, 3 is 4. That is either true or false. In this case, it's true. So that is a statement. Now, if I just said something like R or Z, right, those aren't statements. Those are just sets. I could do a command, add 5. That's not a statement. I could ask a question. What is 2 plus 2? Right, that's not a statement. It's not either true or false. But any sentence or mathematical expression that is either definitely true or definitely false is a statement. So as a practice with that, I want you to go through each of the following statements, and we'll first decide if it's a statement or not. So go through the following sentences, determine if they're statements. If it is a statement, I want you to determine if it's true, if you can, or if you know, or if it's false, or maybe you're just not sure. So go ahead, figure out these ones, and then if you want, I'll get those Jamboard slides posted before class. So on Monday, you can kind of go through and check that out. Put in your answers, and we'll talk about these in class. All right, so let's look at some of the sentences we have and see if we can determine if they're statements, and if they are, if they're true. So the first one says, if x is an integer that can be written as x equals 6n, where n is in z, then x is even. So first we have to ask ourselves, is this a sentence that is either true or false? Well, let's see if x can be written as this, where I have n is an integer, then x is even, right? It's either true or false, so it is a statement. And in this case, it's true. right? If x can be written as an integer multiple of 6, then it's certainly even. I think it's good practice to sort of see some proofs before we actually have to start running them themselves. So I'm going to go ahead and show you what a proof of this might look like. So usually I'm going to start a proof like this by assuming that if expression. So I'll assume x can be written as x equals 6n. That was not an n. With n is in z. And we'll see later when we talk about conditional statements why we might want to assume this. And then next week or the week after when we talk about direct proofs, we'll see what this structure usually looks at. But this is how we usually start a proof for an if-then statement. We're assuming the if. And now I want to show x is even. So again, we're going to need a definition of even. Let's say that I'm going to use the definition that x is even if it can be written as 2 times an integer. So then I'll say then x is equal to 6n, which is equal to 2 times 3n, where 3n is also an integer. Thus, because x can be written as 2 times an integer, x is even. Right? So that is one example of what a proof of this type of statement might look like, just so we can kind of get used to seeing that. Okay, moving back to our discussion of statements, we've got the statement Q, which is the integer x is even. Well, here I can't really prove if this is true or false because I don't know what x is. Right, so this is sort of like a special statement where for some x, it's true, in particular for even x's, and for some x, it's not true. Maybe if x is odd, or maybe, right, we do have that x is an integer, so it's either even or odd, right? I wrote true for both of those. For some x, it's false. So we need some more structure here so we can actually talk about that. And that's what we'll see on the next slide. When I have these things that are like statements, but they depend on a variable, I call those open sentences. So a sentence whose truth value depends on the value of one or more variables is called an open sentence. So if I consider this Q of x that says the integer x is even, that's actually an open sentence instead of a statement. The domain of this open sentence is just all possible values for that input variable. So here, my x is just going to be some integer. That's my domain, is integers. Okay, so for this specific Q of x, one is x true. Well, it's true for the set of x such that x is equal to 2n and n is an integer. So it's true when it is even, and then it's false when for all x in z where x is not equal to 2n. So it's false when it's not even. All right, so we have one more discussion question for you to try here. Consider the open sentence R of f and g that says the function f is the derivative of the function g. So first I want you to think about what the domain of this function is. What type of things is it taking in? And then I want you to find several choices for f and g where this statement is true, and then others where it's false. Right, so once you replace the f and g with a specific functions, that open sentence turns into a statement because then it's either true or false. So find some true statements and find some false statements by picking different options for f and g. To finish up this section, there's a few famous statements, right? So these are things that were provably either true or false, but they either took a really long time to determine whether or not they were true or false, or we actually don't know yet. So I wanted to highlight two of these. So the first one was Fermat's last theorem. So Fermat's last theorem says that The equation x to the n plus y to the n equals z to the n has no solutions in integers, so there's no integers x, y, and z, if n is greater than or equal to 3. Right? So when n equals 2, we know these are our Pythagorean triples, so we certainly do have integer solutions. Right? So for n equals 2, we know that, for example, 3 squared plus 4 squared is equal to 5 squared. But if I think about n equals 3, 3 cubed plus, say, 7 cubed, that's never going to be an integer cubed. So there's no way you can pick 3 integers here, where when you cube 2 of them, it equals the other one cubed. That actually took a really long time to prove, right? So it was conjectured by Fermat in the 17th century, but it was finally proved by Andrew Wiles in 1993. So this is a picture of him next to that equation. The other famous conjecture that we want to talk about is the Goldbach conjecture. This XKCD comic is sort of making fun of that Goldbach conjecture. So it does actually have 2 real forms. So there's the weak form and the strong form. So I'll highlight these are the real ones. The strong form of Goldbach's conjecture says that every even number greater than 2 is the sum of 2 primes. Right? So if I take an even number, say 14, I should be able to write that as a prime plus a prime. It doesn't necessarily have to be distinct, so maybe I can write that as 7 plus 7. Right? For 16, how can I write that? Let's see, I can write 16 as 3 plus 13. Right? So every even number can be written as a prime plus a prime. The weak Goldbach conjecture says that every odd number greater than 5 is the sum of 3 primes. So if I have an odd number, 317, I should be able to write that as 3 primes. It turns out that no one actually knows whether or not these 2 statements are true. Right? They are statements. They're either true or they're false, but no one knows for sure. There's a computer proof. So someone was able to use a computer to try all of the cases they needed to, but it hasn't been checked yet for the weak Goldbach conjecture, so that is still open. For the strong conjecture, no one's really sure. But they're called strong and weak because if you prove the strong one, then the weak one will follow from that. And I'll let you guys think about why that's true. So maybe last discussion question here. Why does the strong Goldbach conjecture imply the weak Goldbach conjecture? The rest of the stuff over here, these are just jokes. And I want you to think for yourself, for each of those jokes, which ones are true and which ones are false.